In this video, we will learn about Design for Six Sigma, DFSS. Common DFSS methodologies. In this chapter, you will learn to list out common DFSS methodologies. Explain design for X, DFX. Explain robust design and process. Explore the special design tools. Common DFSS methodologies. Common DFSS methodologies, section overview and objectives. In this session, you will learn about the following. Define IDOV. Explain DMADV. Describe DMADOV. Common DFSS methodologies. Design for Six Sigma is the suggested method to bring order to product design. It has been noted that 70 to 80% of all quality problems are design related. Emphasis on the manufacturing side alone will concentrate at the tail end of the problem-solving process. The emphasis should be at the front end. Problem-solving at the downstream end is more costly and time-consuming than fixing it at the source. In 1999, it was reported that the automotive supply chain lost at least $1 billion a year due to poor interoperability of digitally designed product data. There has been considerable emphasis in recent years by American industry in downsizing, restructuring, process redesign, and instituting cost containment, etc. These methods are directed at holding the line on costs. This has been described as denominator management. In the business world, the equation for return on investment, or return on net operating assets, has both a numerator, net income, and a denominator, investment. Managers have found cutting the denominator, investments in people, resources, materials, or other assets, is an easy way to make the desired return on investment rise, at least short term. To grow the numerator of the equation requires a different way of thinking. That thinking must include ways to increase sales, increase revenues, introducing more new products for sales to customers. New products account for a large percentage of company sales, 40%, and profits, 46%. Of course, not every new product will survive. Large amount of ideas are needed. These ideas are sorted, screened, and evaluated in order to obtain feasible ideas, which enter the development stage, pass into launch stage, and become successful products. Common DFSS methodologies. Below are details of how winning products are obtained. 1. A unique, superior product. This is a product with benefits and value for the customer. 2. A strong market orientation. An understanding of customer needs and wants exists. 3. Pre-development work. Upfront activities such as screening, market analysis, technical assessment, market research, and business analysis are vital before development starts. 4. Good product definition. A company must undertake good product and project definition before development begins. 5. Quality of execution. The development process has many steps. A company must execute these steps with the proper amount of detail and correctness. 6. Team effort. Product development in a team effort that includes research and development, marketing, sales, and operations. 7. Proper project selection. Poor projects must be killed at the proper time. This provides adequate resources for the good projects. 8. Prepare for the launch. a good product launch is important and resources must be available for future launches. 9. Top management leadership. Management has a role to play in the product development process. They must provide guidance, strategy, resources, and leadership. 10. Speed to market. Product development speed is the weapon of choice, but sound management practices should be maintained. 11. A new product process. This is a screening, stage gate process for new products. 12. An attractive market. An attractive market makes it easier to have a successful product. 13. Strength of company abilities. The new product provides a synergy between the company and internal abilities. Common DFSS methodologies. There are many product development processes to choose from. The former relay race process. One function passing the product from marketing to engineering to manufacturing and back through the loop is obsolete. Multifunctional team activities involving all departments are necessary for effectiveness and speed to market. The process is comprised of two parts: a fuzzy front end, idea generation and sorting, and new product development, NPD. The complete NPD process includes 5 activities. Concept study. A study is needed to uncover the unknowns about the market, technology, and/or the manufacturing process. Feasibility investigations. There is a need to determine the limitations of the concept. Find out if the unknowns are resolvable, or if new research improves the project. Development of the new product. This is the start of the NPD process. This includes the specifications, needs of the customer, target markets, establishment of multifunctional teams, and determination of key stage gates. Maintenance. These are the post-delivery activities associated with product development. Continuous learning. Project status reports and evaluations are needed to permit learning. Common DFSS methodologies. Stage gate process. A stage gate process is used by many companies to screen and pass projects as they progress through development stages. Each stage of a project has requirements that must be fulfilled. The gate is a management review of the particular stage in question. It is at the various gates that management should make the kill decision. Too many projects are allowed to live beyond their useful lives and clog the system. This dilutes the efforts of project teams and overloads the company resources. Product development. Commonly accepted new product terms. 1. New to the world products. These are inventions and discoveries that include products like Polaroid cameras, laser printers, inline skates, etc. 2. New category entries. These are company products that are not new to the world, but new to the company. A Me Too type product. 3. Additions to product lines. These products are extensions of the organization's existing product line. Examples are Diet Coke, caffeine-free Coke. 4. Product improvements. Current products made better. 5. Repositioning. Products that are retargeted for a new use. The original purpose was not broad enough. Arm & Hammer baking soda has been repositioned as a drain deodorant, refrigerator deodorant, etc. 6. Cost reductions. New products which are designed to replace existing products but at a lower cost. The product design development process is described as designing for Six Sigma using the product development process. Best practices include understanding critical to quality characteristics for external customers and internal customers, conducting failure mode and effects analysis (FMEA), performing design of experiments to identify key variables, benchmarking other facilities using competitive analysis, surveys, etc. A standardized approach has not yet been established, but most authors recommend a framework that tries to remove gut feel and substitutes more control. IDOV, Common DFSS methodologies. The 4 steps of IDOV model are: identify, use a team charter, VOC, QFD, FMEA, and benchmarking. Design, emphasize CTQs, identify functional requirements, develop alternatives, evaluate, and select. Optimize, use process capability information, statistical tolerance, robust design, and various Six Sigma tools. Validate, test and validate the design. DMADV, Common DFSS methodologies, DMADV. Simon provides a 5-step define, measure, analyze, design and validate DMADV process for Six Sigma design. The DMADV method for the creation of a new product consists of the following steps. Define the project goals and customer needs. Measure and determine customer needs and specifications. Analyze the process options to meet customer needs. Design, develop the process details to meet customer needs. Verify and validate the design performance. DMADOV, Common DFSS methodologies, DMADOV. The Six Sigma DMADOV process is used to develop new processes or products at high quality levels, or if a current process requires more than just incremental improvement. DMADOV is an acronym for Define, Measure, Analyze, Design, Optimize, and Verify. The process steps for a DMADOV project include: define the project. What are the project goals? Who is the customer and what are their requirements? Measure the opportunity. Determine customer needs and specifications. Benchmark competitors and industry. Analyze the process options. What option will meet the customer needs? Determine creative solutions. Design the process. Develop a detailed process. Design experiments that verify the design meets and customer needs. Optimize the process. Test the new process to evaluate performance levels and impacts. Redesign the process as necessary to meet customer specifications. Verify the performance. Verify the design performance and ability to meet customer needs. Deploy the new process. Summary. Sustain improvements. In this session, you learnt about the following: IDOV, DMADV, DMADOV. Now you should be able to understand methodologies such as IDOV, DMADV, DMADOV. In this video, let us discuss about Design for X, DFX. Design for X, DFX, Section Overview and Objectives. In this session, you will be able to define Design for X, use Design for X tools and techniques, List out the characteristics for Design for X. DFX characteristics. Design for X, DFX. Design for X, DFX, is defined as a knowledge-based approach for designing products to have as many desirable characteristics as possible. The desirable characteristics include quality, reliability, serviceability, safety, user-friendliness, etc. This approach goes beyond the traditional quality aspects of function, features, and appearance of the item. A.T. and T. Bell Laboratories coined the term DFX to describe the process of designing a product to meet the above characteristics. In doing so, the life cycle cost of a product and the lowering of downstream manufacturing costs would be addressed. The DFX toolbox has continued to grow in number from its inception 15 years ago to include hundreds of tools today. The user can be overwhelmed by the choices available. Some researchers in DFX technology have developed sophisticated models and algorithms. The usual practice is to apply one DFX tool at a time. Multiple applications of DFX tools can be costly. DFX Tools and Techniques. Design for X, DFX. The following material is based principally on the work of Watson. Design Guidelines. DFX methods are usually presented as rules of thumb, design guidelines. These rules of thumb provide broad design rules and strategies. The design rule to increase assembly efficiency requires a reduction in the part count and part types. The strategy would be to verify that each part is needed. DFX analysis tools. Each DFX tool involves some analytical procedure that measures the effectiveness of the selected tool. Boothroyd provides a DFA, Design for Assembly, procedure that addresses the handling time, insertion time, total assembly time, number of parts, and the assembly efficiency. Each tool should have some method of verifying its effectiveness. Determine DFX tool structure. A technique may require other calculations before the technique can be considered complete. An independent tool will not depend on the output of another tool. The handling analysis, insertion analysis, and number of parts are all capable of being calculated, but the total assembly time requires subsystem times for each component. Tool effectiveness and context. Each tool can be evaluated for usefulness by the user. The tool may be evaluated based on accuracy of analysis, reliability characteristics, and/or integrity of the information generated. The focus of activity and the product development process. If the product development process is understood by the design team, the use of the DFX tools will be of benefit. Understanding the process activities will help determine when a particular tool can be used. Mapping tool focus by level. The mapping of a tool by level implies that DFX analysis can be complex. Several levels of analysis may be involved with one individual tool. The structure may dictate the feasibility of tool use. For routine product redesigns, the amount of information needed may already be available. For original designs, the amount of interdependence of tools can make it difficult to coordinate all of the changes downstream. DFX characteristics. Design for X, DFX characteristics. The following characteristics and attributes should be considered by the DFX projects. Function and performance. These factors are vital for the product. Safety. Design for safety requires the elimination of potential failure-prone elements that could occur in the operation and use of the product. The design should make the product safe for manufacture, sale, use by the customer, and disposal. Quality. The three characteristics of quality, reliability, and durability are required and are often grouped together in this category. Reliability. A reliable design has already anticipated all that can go wrong with the product, using the laws of probability to predict product failure. Techniques are employed to reduce failure rates in design testing. FMEA techniques consider how alternative designs can fail. D-rating of parts is considered. Redundancy through parallel critical component systems may be used. Testability. The performance attributes must be easily measured. Manufacturability. The concept of design for manufacturability, DFM, includes the ability to test and ship a product. Producibility and manufacturability are terms used since the 1960s. Design for manufacturability, DFM, has been the dominant term used since 1985. A design must simplify the manufacture of a product through a reduced number of parts and a reduced number of manufacturing operations. Assembly. Design for assembly, DFA. DFA means simplifying the product so fewer parts are involved, making the product easier to assemble. This portion of DFX can often provide the most significant benefit. A product designed for ease of assembly can reduce service, improve recycling, reduce repair times, and ensure faster time to market. This is accomplished by using fewer parts, reducing engineering documents, lowering inventory levels, reducing inspections, minimizing setups, minimizing material handling, etc. Environment. The objective is minimal pollution during manufacture, use, and disposal. This could be defined as Design for the Environment, DFE. The concept is to increase growth without increasing the amount of consumable resources. Some categories of environmental design practices include recovery and reuse, disassembly, waste minimization, energy conservation, material conservation, chronic risk reduction, and accident prevention. Serviceability, maintainability, and repairability. A product should be returned to operation and use easily after a failure. This is sometimes directly linked to maintainability. Maintainability. The product must perform satisfactorily throughout its intended life with minimal expenses. The best approach is to assure the reliability of components. There should be reduced downtime for maintenance activities, reduced user and technician time for maintenance tasks, reduced requirements for parts, and lower costs of maintenance. NDRES provides some specific methods for increasing maintainability, decreasing diagnosis and repair times. Use modular construction in systems. Use throwaway parts instead of parts requiring repair. Use built-in testing. Have parts operate in a constant failure rate mode, etc. User-friendliness or ergonomics. Human factors engineering must fit the product to the human user. Some guidelines to consider are fitting the product to the user's attributes, simplifying the user's tasks, making controls and functions obvious, anticipating human error, providing constraints to prevent incorrect use, properly positioning locating surfaces, improving component accessibility, and identify components. Appearance, aesthetics. Attractiveness is especially necessary for consumer products. These characteristics include special requirements of the user, relevancy of the style, compatibility of materials and form, proportional shapes, or protection from damage in service. Packaging. the best package for the product must be considered. The size and physical characteristics of the product are important, as are the economics of the package use. The method of packaging must be determined. Automated packaging methods are desirable. Features. Features are the accessories, options and attachments available for a product. Time to market. The ability to have shorter cycle times in the launch design of a product is desirable. The ability to produce the product either on time or faster than the competition is a tremendous advantage. Summary. Common DFSS methodologies. In this session, you have learnt about Design for X, Design for X tools and techniques, Characteristics for Design for X. Now you should be able to understand the Design for X methodology and also its characteristics. In this video, let us learn about robust design and process. Robust design and process. Section overview and objectives. In this session, you will learn to define robust design and process. Describe the approach for robust design. List out the key principles of robust design. Explain Taguchi's quality imperatives. Introduction. Approach. Robust design and process. Introduction. Robust design introduction. Dr. Genichi Taguchi wrote that the United States has coined the term Taguchi methods to describe his system of robustness for the evaluation and improvement of the product development processes. He has stated that he preferred the term quality engineering to describe the process. Other authors have used robust design or robust engineering to describe the process. Any of the above-mentioned terms can be used. Quality engineering will be the term used when material is referenced from Taguchi's text or articles. In this section, robust design will be the main term of choice. Robust design approach. Robust design processes are one of the more important developments in design processes in recent years. The use of robust approaches for design is a process that, when used, can produce extremely reliable designs both during manufacture and in use. Robust design uses the concept of parameter control to place the design in a position where random noise does not cause failure. The concept is that a product or process is controlled by a number of factors to produce the desired response. The signal factor is the signal used for the intended response. That is, the actions taken signal to start the lawnmower response, or the dial setting signal to obtain a furnace temperature response. The success of obtaining the response is dependent on control factors and noise factors. Examples of noise factors in furnace design include tolerance design, outside temperature, parallax errors in dial setting. The noise factors have the ability to produce an error in the desired response. The function of the designer is to select control factors so that the impact of noise factors on the response is minimized while maximizing the response to signal factors. This adjustment of factors is best done using statistical design of experiments, or SDE. Key principles. Robust design and process. Key principles. Some of the key principles are concept design. Concept design is the selection of the process or product architecture based on technology, cost, customer, or other important considerations. This step depends heavily on the abilities and creativity of the designer. Parameter design. During the parameter design stage, the design is established using the lowest cost components and manufacturing techniques. The response is then optimized for control and minimized for noise. If the design meets the requirements, the designer has achieved an acceptable design at the lowest cost. Tolerance design. If the design doesn't meet requirements, the designer begins considerations of more expensive components or processes that reduce the tolerances. The tolerances are reduced until the design requirements are met. With robust design approaches, the designer has the ability to produce a design with either the lowest cost, the highest reliability, or an optimized combination of cost and reliability. Functional requirements. In the development of a new product, the product planning department must determine the functions required. The designer will have a set of requirements that a new product must possess. The designer will develop various concepts, embodiments, or systems that will satisfy the customer's requirements. All possible alternative systems should be considered. The alternative systems include existing ones and new, not yet developed systems. The criteria for selection of a design will be based on the quality level and development costs that will enable the product to survive in the highly competitive marketplace. The product design must be functionally robust, which implies that it must withstand variation in input conditions and still achieve desired performance capabilities. The designer has two objectives: develop a product that can perform the desired functions and be robust under various operating or exposure conditions. Have the product manufactured at the lowest possible cost. After selection of the new system, the nominal values and tolerance parameters of the new system must be determined. The optimal solution to the new system is called the optimal condition or optimal design. Parameter design. Parameter designs improve the functional robustness of the process so that the desired dimensions or quality characteristics are obtained. The process is considered functionally robust if it produces the desired part with a wide variety of part dimensions. Signal-to-noise ratio. A signal-to-noise ratio, S/N, is used to evaluate system performance. In assessing the result of experiments, the SIN ratio is calculated at each design point. The combinations of the design variables that maximize the SIN ratio are selected for consideration as product or process parameter settings. Taguchi's quality imperatives. The following is a paraphrase of some of Taguchi's robust design principles. Robustness is a function of product design. The manufacturing process and online quality control cannot do much to change that. Quality losses are a loss to society. Robust products have a strong signal with low internal noise. The design change of increasing the signal-to-noise ratio will improve the robustness of the product. For new products, use planned experiments varying in values, stresses, and conditions to seek out the parameter targets. Orthogonal arrays are recommended. To build robust products, simulate customer use conditions. Tolerances are set before going to manufacturing. The quality loss function can be measured. Products that barely meet the standard are only slightly better than products that fail the specifications. The aim is for the target value. The factory must manufacture products that are consistent. Reduced variation is needed for consistency. Reducing product failure in the field will reduce the number of defectives in the factory. Part variation reduction decreases system variation. Proposals for capital equipment for online quality efforts should have the average quality loss function added to the proposal. Summary. Common DFSS methodologies. In this session, you have learnt about the following: robust design and process, approach for robust design, the key principles of robust design, Taguchi's quality imperatives,